hopefully will get you excited about this area if you're not already excited. And then I'm going to review very briefly some of the exciting ideas that are going on right now in terms of how to tackle JT gravity using techniques from matrix models. For me, the thing that's really interesting is that there's an older language, which actually many are not familiar with because it's been forgotten, an older language from the 1990s, going all the way back there, that seems to fit extremely nicely with what's going on now. And in particular, I think is very well suited to giving non-perturbative insights into some of the things that people are working on. And hopefully by the end of the talk, you will be convinced, because I'm going to show you, and you're the first audience to see this, I'm going to show you some really lovely non-perturbative results for some very important quantities. Okay, so let me just check when I started. Okay, good. So let me jump through some of this. So one of the things that's really quite exciting is the fact that JT gravity is at the center of a lot of different ideas intersecting in various ways, including black hole physics in higher dimensions and in 2 dimensions, ideas like quantum chaotic systems, SYK-like models, things like that, entanglement, wormholes, quantum teleportation, connections using gauge gravity dualities to get insights into those things, and large N matrix dynamics, which we'll talk a little bit about as well. Very briefly, the action looks something like this. The picture I have above, the yellow thing, is really meant to be some sort of 2-dimensional space-time. I'm including the possibility that it has all kinds of interesting topology as counted by having boundaries, handles, and crosscaps in the case of non-orientable surfaces. I'm working in the Euclidean signature right now. The action looks something like this. There's pieces talking about the main bulk, M, and also the boundary. And essentially, as you know, in 2 dimensions, there's not really any dynamics going on in the gravity. However, because we have a scalar, actually, some exciting things can happen. And one way of thinking about it is to think about one way of, oh, can't find my pointer. No. Well, that's annoying. The cursor seems to be missing, so I can't actually point the way I thought I would. Okay, well, I'll just tell you where I'm looking. I'm looking at the fact that phi is coupling to the Ricci scalar +2 in the middle of the board there. And so the equation of motion for phi essentially tells us that we're on locally ADS2 like spaces. And then there's some interesting dynamics on the boundary, which was shown. And apologies to lots of people for all the work that I'm not citing appropriately here, just to quickly move through. But the boundary dynamics has a Schwarzian action, which you can see at the bottom there. And the picture you should have in mind is that there's some ADS2-like space, which I've drawn in green, which normally would be, for example, the Poincaré disk in the way I've drawn some coordinates up above, going all the way out to infinity. But actually, the dynamics think of as being on a boundary just inside that asymptotic boundary, that yellow boundary I've drawn, which can fluctuate. And that fluctuation is the dynamics, and that's what the Schwarzian dynamics is controlling for you. So this is what's often referred to as an almost or nearly ADS2 space-time, and in the sense that there is some length of that boundary, which is of length beta, which is the inverse temperature. And so that is finite. Remember, in ADS2 on the Poincaré disk, if I went all the way out to infinity, I would have a boundary of infinite length. So it's infinite beta. It's just inside. It's wiggling. That defines the temperature of the system. And you can compute a partition function. And so a wonderful place to learn about some of this would be, for example, Shenker and Stanford, who put a lot of this story together in relation to both the gravity side and the dual SYK model. And then there's Christian Jansen and a number of other authors who first began to put this picture together. Okay, so there's a nice sort of black hole picture of all of this that is worth thinking about as a way of motivating it all. And this is the sort of picture that you may be familiar with. For example, if you have a four-dimensional black hole that's charged, it's, I think, well known, maybe one of the first near horizon geometries anyone ever writes down is the fact that the near horizon geometry of Reisner-Nordstrom is ADS2 cross S2. The area of that S2, the area of the horizon, is set by some charge, and that defines the entropy in the usual black hole thermodynamics. And the picture you have in mind, you should have in mind then, is that if you were to move away from zero temperature extremality slightly away, you would have a deformation of that ADS2, and in some ways JT gravity is capturing precisely those dynamics. The scalar, if you like, is parameterizing deviations of the area away from the extremal value. And the dynamics then is the wiggling of that boundary. So I have some small temperature dynamics, which I've drawn in that box there. You can go ahead and use the partition function that I wrote on the previous page to compute the entropy in the usual way, and see then that you have a leading entropy, that S0, which I had in the action previously, which was just a parameter, the leading entropy. And then there are deviations away from the entropy, a linear deviation in temperature, and the logarithmic correction, and so on and so forth. So that's one way of connecting this to things we know from high-dimensional black holes. What I want to talk about a lot today is the spectral density. Essentially, there's really not much going on besides the temperature set by beta and the coupling S0. And so what I have is I can do a Laplace transform and write down, instead of dependence on beta, I can write down the dependence on energy via Laplace transform. And the Schwarzschild dynamics gives you this nice function, this cinch. Still trying to find a cursor. I may, can anyone actually see a cursor?
No.
I think you have to move it a lot and then it appears. At least that happened to my computer.
Yeah, it's weird. When I went into full screen mode, it sort of disappeared. Yeah, thanks for the suggestion. I don't see, I can see that it touches things, but the actual thing itself is missing. Okay, I have a version of this on my iPad. I wonder if I should just move to that. Okay, let's see how we go. If it becomes too unclear what I'm pointing at, let me know and I'll jump to a different device. Okay, so there's the this cinch function here is what results from doing that Laplace transform. And what I want to do is to think about it in terms of its constituent powers of E. I'm just going to do this expansion in terms of, and so it starts out with root E, and then there's E to the 3 halves, 5 halves, etc., etc. And there's a reason I'm going to do this, and you'll see it's a rather cute way of decomposing everything in a moment. So generally, I have e to the some fractional power of e to the k minus a half, where k is an integer. Generally, I can sketch that function, and there it is. Looks something like that. And what I'm going to do is actually look, first of all, at the very leading edge, the tail of the distribution, which just goes like e to the half at the bottom there. And we're going to focus on that for a while because it's going to be a prototype of some of the things I'm going to tell you about. But before we go any further, let me just say a couple of interesting things. So far, we have then this picture, which I'm going to draw like this. I'll sometimes draw these little sort of cone-shaped things to tell you there's the boundary, that the circle of the cone, and then the interior, which is some sort of ADS to sort of bulk. But I also want to consider, as I said before, other topologies. And in fact, higher topology is going to be extremely important, not the least because you'll want to consider diagrams like that double cone, that sort of deformed cylinder that I drew there, in order to understand diagnostics of chaos in the quantity I hopefully will get to at the end, the spectral form factor. But also, it's interesting to study higher topology because this is a toy model of quantum gravity, and it's always good to understand toy models of things that we consider important. So let me tell you about a piece of technology from some time ago, which is relevant to this. And there are various ways, going back to some earlier papers in 2016. I'm blanking for a moment. Okay, I'll move on. That began to suspect that there may be a way of describing some of this in terms of matrix models. And there's a large group from Stanford, Kotler et al., and but there's also Garcia et al. As well, I think. And it all culminated in this beautiful paper from last year by Saad, Shenker, and Stanford. But before I get to that, let me remind you of some older stuff. The key thing is that you're doing these random matrix models in what's called a double scaling limit. And it goes back to observations, for example, by Thorst, which says that if I have some model of a matrix, in general, he was thinking of QCD, slightly more complicated matrix model. But the idea then is a large N expansion of some matrix valued field theory is a way of capturing topology. You can actually think of things as organized in a 1/n expansion, and this was developed very well later on by other authors into a tool for studying two-dimensional surfaces. And so what I've drawn is a couple of examples. If I just took that field theory I wrote down there, which essentially field theory is a bit strong. It's just a matrix with a potential V, and I can draw Feynman graphs as I normally would. And if I organize things in terms of powers of n, the leading large n terms can be drawn on the sphere, and you have diagrams that you can't draw on the sphere, and at order n to the -2, you can actually draw them on the torus, and so on and so forth. The double scaling limit then says take a large n limit of one of these models, but at the same time tune the couplings and the potential in such a way that you're not just getting all surfaces. You're actually you're interested in large surfaces that will ultimately be large, smooth surfaces that, when you take the right limit, will correspond to the continuum surfaces of the gravity theory you're trying to capture. That double scaling limit then yields for you a theory which sort of creams off the good stuff from this model and yields quantities that then capture the continuum physics. very, very briefly, what you typically do when you do these calculations is you diagonalize the matrix. There's a Jacobian, a van der Waals determinant for doing, in exchange for doing that, working in the diagonal variables, which I've called the eigenvalues of M, which I've called E tilde. And you end up with something like this. And the way you should think about this is that you then have this one-dimensional problem, the space E, where the eigenvalues, the energy eigenvalues live. And essentially solving the problem boils down to solving the following. I have the potential, the original potential V, which I've drawn in blue there, which tries to confine these eigenvalues. But the Jacobian, the van der Waals determinant, is a repulsive term that then pushes them out, and there's some balance where they form some sort of droplet, and that's what you can solve for at large n. And what you actually do when you solve at large n, but you also go to the double scaling limit, is what you're really doing is you're focusing on the very tail endpoint of that eigenvalue density, and that's what that corresponds to. And I wanted to get to that picture because visually that's all I need. That's all you need to know for today for what the double scaling limit is if you haven't encountered it before. A most famous example for lots of reasons is the Gaussian case, where I just have a quadratic potential. When the dust settles, you get the famous Wigner semicircle law for the eigenvalue distribution rho of E tilde, which looks like this. I've drawn it in perhaps slightly unusual parameterization in that I've put the end at 0 instead of having the thing straddle 0, which is usually how it's presented. But that allows me to quickly get to where I need to get, which is that so rho looks something like that in these coordinates. There's some size set by A, and then zooming in on the end, as I said, looks something like this. And there you see I have rho goes like e to the half. There's some pi there in my coordinates. And what I've done, I've now come to coordinates e without the hat. These are the double scaled energies, which is what we were talking about all along. So more generally, I should say, going back to the late 80s, early 90s, you can do a lot more than that. You can find what are often called multi-critical potentials in those days, which when you tune, you have an eigenvalue density that looks like e to the some other fractional power of e at the tail, and so I'll parameterize it as e to the k minus a half. So these were the old matrix models, and in those days, they were useful for studying two-dimensional quantum gravity as string world sheets, and they were actually, it turned out, the two k-1 conformal minimal models coupled to two-dimensional quantum gravity. These are quite different in some ways, matrix models, from what Triple S, Saad, Shenker, and Stanford constructed. But what I'm going to show you is that in some sense, I can build the new stuff out of this old stuff. Now, one of the things that was exciting about the 1990s was the fact that those matrix models gave you more than just perturbative information. They gave you non-perturbative information about the quantum gravity theory. So a lot of what I've been thinking about in the last several months has been the idea that if I can build the Triple S matrix model out of these old minimal models for which I have a good understanding of the non-perturbative physics, then I can get at the non-perturbative physics of the Triple S matrix model, and hence JT gravity. So let's head back to JT gravity and write things in the following form. In general, then, I'd like to have topological correction to the partition function, or by extension to the spectral density. If you go back to the action that I wrote down originally, there was an S0 in front of the Einstein-Hilbert term, which in 2 dimensions gives you the Euler number, and things organize themselves in the following way. So I have this expansion that comes with powers of e to the minus S0, which henceforth I'm just going to call h bar. And that will be appropriate as well, because it'll be the h bar of a theory that where it really is quantum mechanics. So there are perturbative terms, and then there are also non-perturbative pieces. And in fact, the beautiful work of Triple S last year, and then followed up by Stanford and Witten a couple of months later, was telling you how to build for various kinds of JT gravity, telling you how to build the whole perturbative series in topology. But almost by construction, they don't give you much insight into the non-perturbative work, which is why I've been thinking about this sort of stuff. They essentially write down and invoke the existence of the matrix model and show that it exists perturbatively by actually writing recursion relations, which you can derive in general from a matrix model. Even if you don't know the detailed potential, you can write down, given the potential, you can write down a family of recursion relations, which tells you how to relate different orders in the topological expansion. And those turn out to have a great and beautiful connection to various things that mathematicians had been doing, such that you can then, on the JT gravity side, actually do the order by order topological calculation on various surfaces, compute JT gravity, and see that the recursion relations are indeed telling you things about, they're consistent with how JT gravity is organized. And then the recursion relations essentially tell you all you need to know is the sphere level, sorry, the disk level, rho 0, which we already have from the Schwarzschian. Tells you all you need to know is what that is, and then the recursion relations will essentially build the entire topological expansion for you. And so roughly speaking, that's what they did. And so the JT matrix model then is defined as some actually Hermitian matrix model, which is a set of recursion relations and the leading order rho 0. It's some double-scaled matrix model that you can't explicitly write down the analog of the double-scale potential that you would do in a simple toy model of the sort I just showed you. Although I'm going to show you how to do that in a while. So what I'm here to tell you mostly is that there's another way of doing this. So and it looks like this. So this goes back to some very old technology. It turns out that rho that we've been talking about is a spectral density in an associated one-dimensional system, and this has been known for a large class of matrix models, double-scale matrix models from again the old days. There's an associated Hamiltonian problem. There's the Schrödinger Hamiltonian with some potential u, and if you solve the spectrum of H, the eigenvalues and eigenfunctions, and construct the spectral density I've written there in the middle, where I integrate over x from minus infinity to 0, I will build this spectral problem, which will indeed be and I'll show you how to do it in a moment, which will indeed be the same spectral problem that we're trying to solve from JT gravity. So I can do this for any one of those simple matrix models. And looking ahead, what I'm going to do is I'm going to show you how to build the U that you need in order to construct the entire U for which would be the matrix, which would tell you about the matrix model for JT gravity. If I solve that spectrum fully to all orders, then I will construct non-perturbatively the entire partition function for JT gravity and various variants thereof. But before we do all of that, let's study a simple example, and that's the Airy model, which is indeed this low energy tail that I was telling you about. So there's a family of equations that the matrix model comes with that tells you what the potential U is. And in the very simplest case, or actually one of the very simplest cases, the very simplest case in the case of Hermitian matrix model, the potential is minus U. That's right, minus X. U is minus X. It's just a line of a slope minus 1. If I stick that into the Hamiltonian problem, after change of variables, you realize it's just defining the wave functions to be the Airy functions. And so they look like that. There's psi of X and E at a given E. And so the picture you should have in mind is that I have, at a given energy, I have a psi that looks something like that. It's oscillatory far away, and then there's some exponential tail when it hits, when the energy matches U, and then quantum mechanically we can penetrate into the barrier like that. So I can go ahead and I can compute the spectral density, and if you remember your technology of Airy functions, you'll see at leading order there's a dependence just at the bottom of the page. It goes something like that. If I plug that in, I'll get the e to the half, and I've normalized the Airy functions in just the right way to match the normalization I had before, and I get the e to the half behavior for the spectral density. So in this little toy model, this is the disk. This is the analog of the Schwarzian in the full JT gravity, except it's just this toy model, the Airy model. Let me tell you. Let me digress a little bit about to give you a hopefully helpful picture about how to work with some of these quantities. At leading order, the potential, whatever it is in general, there's some function of X, U, and at leading order, there's some simpler function, which I'll call U naught of X, which is the thing that just tells you about the disk level. And so if I work with that, I will have the spectral density for just including the disk order contributions. And it turns out I can write it directly in terms of potential, in terms of this integral. And that might look a little bit mysterious. Again, it's some old technology that everybody knew once upon a time, but but hasn't been used a lot. So let me give you a picture for how that works. What I have is I have some sketch of the potential U, or U naught of X. It's the disk level potential. It looks something like that. There's some energy that I'm interested in, and then in yellow I've shown you the difference between E and U naught, and that's what goes into the integral on the bottom line, square rooted. And then the integral I do is I integrate from minus infinity all the way up to 0, which is where the potential goes to 0. Or more correctly, I'm integrating from, I can do that integral, but I just take the real part, if you like. So the square root is not giving me an imaginary piece. And so if I do that for all energies, I build then that function rho of E, which is the spectral density. And so that's one way of thinking about that. Another useful trick is to realize that I could change variables in the integral and work instead with U. So I have some Jacobian, which is just f of U. I throw in an additional minus sign so that I have the integral going from 0 to E, keeping things real, f of U du naught. And that integral then is something that arises extremely naturally in this language. You can think of it as telling you, and there's an associated problem involving resolvents and a thing called the Gelfand-Dickey equation, where you can derive this directly, the leading order part of that. And you're essentially telling you that the spectral density is supported on the square root branch cut in the E plane, which looks something like this. And the fact that the branch cut runs from 0 to infinity is very much in line with that picture that I showed you, where I have, when I zoomed in to the end of the eigenvalue distribution in the matrix model, the end of the energy distribution, even though it was a finite sized droplet before double scaling, once I zoom in at that endpoint, it's essentially half runs over the half line, which corresponds to this branch cut here. So I've gone a little bit off track there, but it'll give me all the pieces I need to tell you how to build things rather efficiently. So more generally, then the spectral density is built like that, and if I represent the partition function, going back, writing it in terms of Laplace transform like that, you can actually see that a very nice shorthand way of writing what the partition function is by essentially doing, plug that row into that Laplace transform and work backwards, and you'll see that it essentially looks like this. The partition function, which would be the partition function of our JT gravity if we had the right potential, is the trace of this exponentiated Hamiltonian e to the minus beta h with some projector inserted, and that projector really is telling me that I integrate from minus infinity up to this place where the potential ends, where the potential hits zero. Well, classically, that's the picture I showed you just now. And you can actually prove this by inserting a complete set of states in the way I've shown you at the bottom right, and unpack that thing in the yellow box and go backwards to show what I just showed you. More generally, because I'll need this later on, this is an extremely efficient way of organizing how to make higher correlators of Z, which we'll need to make things like the cylinder diagram. And essentially, you insert several of these exponentiated Hamiltonians into the trace, separated by projector, that same projector in the way I've just shown. And so I'll come back to this, I hope. Or if I don't come back to this formula precisely, just have in mind that this is the thing you would use to construct the connected contribution to the correlator of two partition functions. This is the thing you would need to construct the spectral density, the spectral form factor. Okay, so I think I can skip. I was going to show you this another way, but I'm just going to skip this. So let's, this is going to be a nice prototype for what I'm going to do with higher powers of E. So let's go ahead and do this. Just working at the disk level with this formula that I told you for, if I know the potential U naught, I can build rho naught. There it is. And you can see how to make it work. If I have U naught equals minus X, and I plug that in, it immediately gives you e to the half. And the point is that those minimal models I was telling you about before from the old days, their leading sphere contribution looks like the following. Instead of minus X, I have minus X to the 1 over K. And if you plug those in, you'll get that rho goes to e to the K minus a half. And so that is the key I need to tell you how to build JT gravity out of minimal models. But where do those things come from? Where does that equation for the potential come from? And that's the core part of the double scaling limit from these old Hermitian matrix models, which is that they give you what's called a string equation. They give you a nonlinear differential equation for U. That's what comes out of the double scaling after all the hard work, which succinctly captures all of the physics. And the case model has a dependence that goes, as I said, minus X to the 1 over K. There are corrections to that. Those are the topological corrections, and they are captured by the string equation, which looks roughly as follows. I have this object which I'm calling RK, which is some polynomial in U and its derivative. If I drop derivatives, it turns out I just have U to some power, and that is the disk level. Including those derivatives captures all of the corrections in topology. In general, I can couple together different minimal models. If you like, what it means is I'm in one given minimal model, and I turn on operators that flows me in the direction of some of the others. And I turn those on by turning on coefficients T little k, T subscript k. And so the general string equation simply just looks like Tk times Rk, this linear combination at this level, which ultimately gives you this highly nonlinear combination of all the potentials by virtue of having to solve the coupled differential equation that is on the page there. What I'm going to do later on is show you that I can solve that coupled differential equation. In the case that I was just looking at, k equals 1 just gives you the leading airy model. In general, if I turn k equals 1, turn on tk equals 1 and turn off all the other tks, then I have the simple model. Or I can turn on any particular one by turning off all the other k's. Or I can turn them all on in different combinations, and that's what we're going to do now. Because you see, if I want to build the Schwarzian Finch function, I now have a recipe. And this was pointed out by Okuyama et al. Last year. The recipe is as follows. I just need to figure out what the function f is, that if I put it in there, will give me that sinh of the Schwarzian. That sinh of the Schwarzian is built out of powers of e to the half. And I know individually that each of those is built from a U of the form that the minimal models give me. And so it's just a bit of algebra to see what combinations, what TKs do I turn on? In what combination do I turn on the minimal models in order to build this thing? And it turns out rather nicely that you can write this in my notation. It's the combination TK written there, pi to the 2k minus 2, etc. I still can't point, so I'm just letting you know where it is. The second line. Okay, so that's rather nice, and there was a factor of 2 I had wrong, which I realize I've now fixed. So that was sort of a note to self, just ignore that. Okay, so that's rather nice. And I like to draw is the following. Well, let me first say that Saad, Shenker, and Stanford had already noticed that there ought to be some kind of relationship to minimal models, and they proposed that there was some sort of large k limit of a minimal model that you should take, and I don't think that's wrong. I think that there's some sense in which that makes sense, but I think you need to say things a little bit more carefully, and I think this is one way of saying things more carefully. And so the way I like to think of it is as follows. You work with the case model, which looks something like that. It's that in the center. That is the model you're going to sort of take to infinity. But you also turn on all the lower k models at the same time in some particular combination. And that corresponds to doing, for example, an RG flow, where I turn on a family of operators in the model. And then I turn on that particular combination as I go to infinity. And if I do things right, I'll get some good physics. And so indeed, what I'm doing is using that as a non-perturbative, the foundation for then doing more than just perturbation theory, which is what Okuyama et al. Do in this language in a couple of written beautiful papers. I want to get at the non-perturbative stuff. I want to get the whole story. Let's talk about non-perturbative physics. Going back to the airy model as an example. So what I have the full wave function. So I can and all the energy. So I can actually construct the full spectrum. And if you do it, it's built out of Airy functions in the following way. These are fairly elementary integrals you can do with Airy functions. And if I expand things out, there's the leading e to the half, and then there's some other powers of e, and then there's non-perturbative pieces as well. And that's all very nice. And if you actually worked it out, it looks something like this. I plotted it for various reasons. There's the dashed line is the e to the half leading disk level contribution, and then the full non-perturbative physics has a large e. It has that e to the half, but then as it comes in, it develops these undulating wiggles, which amplify as you come down to zero energy. But actually, and this is a generic feature of the Hermitian matrix models, there are non-perturbative corrections that take you into e less than 0 as well, which for the k-even models is actually not good. It represents a non-perturbative instability. This is sometimes in Triple S's paper referred to as the forbidden zone, when you have an exponential tail into the forbidden zone, which for many things doesn't matter in perturbation theory, but actually secretly telling you that there's something dangerous going on, which could be destabilizing your whole model. What it's essentially telling you is that eigenvalue distribution that you solve for is secretly wanting to tunnel to a whole new configuration, and due to eigenvalue instantons. And so it's telling you that you're doing perturbation theory about an unsafe vacuum in some sense. It's easy in this picture with potentials and things like that from minimal models or whatever. It's very easy to see how this stuff is organized. And it's one of the reasons I think this language is extremely powerful. That integral I was telling you to do essentially comes in from minus infinity and stops at 0 and builds row of e, but inevitably it's picking up tails of look in the bottom left-hand corner. It's picking up tails of Airy functions from negative energy that are tunneling in as they are wont to do, because it's quantum mechanics, into that region at positive x, and thus producing those contributions. And I'm just going to skip a little bit because I don't want to take too much time. So all sorts of things happen, blah, blah, blah. This is the clue for actually how you would fix the non-perturbative problems, which is what I first started thinking about in this context in a paper last December, which is that find a way of actually not having wave functions coming in that negative energy region. You wouldn't have those tails, and you wouldn't have those exponential instantons telling you about tunneling to a different area. It turns out that there's another set of minimal models which are very, very perturbatively speaking, very similar to the minimal models I was first telling you about, but actually they are they have a different origin. They're from what are called complex matrix models. I double scale a certain family of complex matrix models, and in fact they go back to work I did, actually feeling very old now, work I did for my thesis work back in the early 90s. They satisfy a larger, the string equation is essentially all you need to know for how they work here. And they satisfy a larger equation which looks like this. So capital R is shorthand for the object that I saw earlier, that I showed you earlier. R is built out of RK plus X. If I set that R on its own to 0, that corresponds to the string equation that I was solving before for the Hermitian matrix model. But more generally, if you solve the equation in the red box, there are other kinds of solutions. And so you have solutions that look like this. They go like minus x to the half, minus x to the 1 over k in the region, in the negative x region. So that matches on to what we had before. But in the positive x region, they actually go to 0. And you can see that this is rather nice because assuming that there are no bound states, and it turns out that they don't seem to be, and I did a lot of work on that some years ago. It turns out that that little well is safe. It's not producing any negative energy state. It turns out, and here's an actual solution of the equation. Goes to a hand drawn sketch. That's for k equals 1. That's for k equals 2. It turns out that you can solve this problem instead. And if you look, you'll see, for example, that I have at high enough energies, it looks very much like the Airy case. It goes linear far out because it matches that minus x perturbation theory to the left. But then as I come in to lower energy, it deviates from the Airy problem and becomes something more interesting. And if you actually go ahead and solve that problem, as I did, you'll see that the spectrum is what you might anticipate. It ends at equals 0. It has a lot of similar character to the Airy problem, but then actually stops at equals 0 and doesn't have that unpleasant non-perturbative sector. So this was this was essentially the key that I needed, the clue I needed to learn how to build non-perturbative definitions of JT gravity that do not have the kinds of problems that JT gravity seems to have if you build it out of emission matrix models. That having been said, in a paper that should come out on Monday, I think the story is far more interesting, and I think there's a class of solutions of emission matrix models that that may actually produce some very interesting non-perturbative, safe non-perturbative physics that haven't been used in this context that I think I'm able to find, but I don't have time to tell you about that. So I'm going to skip some things about walls and eigenvalues and things like that, and just go back to this equation and linger here for a moment, because I'm going to now change tack a little bit and tell you about a family of JT gravity models, very briefly, a family of JT gravity models that actually don't have the kinds of subtleties that that are present here, and in fact naturally use this equation with a slight generalization as their foundation for writing in terms of minimal models. So I think at this point I'm going to jump to a different device and just sketch some things. While I do that, are there any questions? Because I may have gone a little quickly on some aspects. Okay, I'll take that as a no. There are no questions, and hopefully you can see the following screen.
Yep.
Yes, you can see this. Okay, excellent, good. Right. So what I wanted to do, because time is short, and I think sorry. Make sure I have the right. Okay, good. I wanted to just tell you very briefly that so there's this paper of Stanford, no D, Stanford and Witten from last year, You can look up the precise references in my paper. They actually took this picture of ordinary JT gravity, which so via SSS, it's some Hermitian matrix model. So some random Hermitian model of random Hermitian matrices, if you like, a Gaussian unitary ensemble is the language you would use there. And they realized you could classify a whole bunch of more JT gravities. So that includes a JT family of JT supergravities and others. In terms of the fact that there's a whole bunch, in fact, 10 random matrix ensembles. So three of those are what's called the So the Gaussian unitary ensemble is 2, and there's a 1 and a 4 in the Wigner, the Dyson-Wigner classification. So usually these Hermitian matrix models, orthogonal and symplectic matrix models. But then there's 7 more, which are classified by Outland-Zernbar. I can't spell today. And there are 2 indices used for that, alpha and beta. Beta refers to essentially the power of the van der Waals determinant in the Jacobian when you do the diagonalization of the matrix model. And alpha is some additional power that comes in the Jacobian as well, some additional power of lambda. So what I'm going to do today is tell you, well, I won't have time to show you, but one of the things I discovered to my delight earlier this year was that the case alpha beta equals 0, 2, and 2, 2, which had some very, very special features in the paper of Stanford and Witten, which are a kind of JT supergravity. They are in fact captured quite nicely in terms of this picture that I've been pushing about building things out of minimal models. I was able to show that a particular family of minimal models, the ones that solve this equation that I wrote earlier, there's an actual additional parameter called gamma, which goes there, and gamma is a half. It turns out if you write this down, I've suppressed a set of parameters to 1 just for ease of writing. It turns out that the 2 gamma plus 1, 2, sorry, alpha beta equals that. And so in the case of gamma equals 1/2 or minus a half, you land on the 0, 2 and 2, 2 models. And I showed precisely how you can build everything out of that. The key there is that in that case, the spectral density for the super JT model looks like 1 over the square root of E times the hyperbolic cosine up to some factors. That's the leading disk contribution to the partition function. So you can pretty much play the same game that I talked about in the Hermitian matrix model case, right? Expand this in powers of E, and it tells you essentially what combination of the minimal models you need to do in order to build the model. This is a very different kind of model because you have, in addition to positive, you have e to the half plus higher powers, but it actually starts out with a 1 over e, which is something you do not see in a Hermitian matrix model. And the really nice thing that I realized was that 1 over root e that everything leads off with is precisely, there's the potential, there's the e to the k minus a half type behavior, sorry, there's the minus x to the 1 over k type behavior in that direction. That's common to both kinds of models, which will eventually yield the e to the k minus a half piece. But this leading u equals 0 part down here that these solutions have, that new piece, is precisely, if I go back to rho equals 1 over e minus u0 to u0, that's precisely what gives the 1 over root e behavior that you need for the super JT type model. So in that way, I was able to find a different combination of TKs, which I won't bother you with the formula right now. Actually, it's pretty easy. It's k factorial squared, 1 over k factorial squared, and pi to the 2k. If I build the matrix model, if I build a potential out of that, and I have knowledge of the full non-perturbative solution of the equation, which look roughly like that, then in principle I can build the super JT gravity model completely, including all its non-perturbative contributions. So in the remaining time, I think I have 5 minutes left. I'm going to show you a couple of fun. I'm going to show you some results. The big obstruction to all of this is the fact that what I'm doing is I'm turning on an infinite number, right, in this object R, tk, rk plus x, which then plugs into this even bigger equation involving r's and its derivatives that I showed you before. This thing here is the k equals 1 to infinity. This thing has powers of u to the k, and high derivatives of k, 2k minus 2 of them. And so it looks like in order to really solve this, I've just done a formal exercise. I have an infinite order. ODE to solve, which in principle doesn't really get me anywhere. Until you realize that actually the formula I'm giving you for the TKs, for example, as I get to higher and higher TK, actually the contribution of those really high orders in that differential equation are much smaller than some of the leading lower parts. So there's a sense in which I can truncate this problem. For a given question that I might want to ask, practically, there's the, in principle, full potential that I don't know, but actually it looks something like this, with all of the TKs turned on. And that would be the solution to this quote unquote infinite order differential equation, which of course would seem to be accessible. But if I'm asking a question at some particular energy, then it's enough to know the solution well at energies below here. And if I can make this large enough, this energy that I'm looking at, then by the time I'm out in this region, I'm actually back in just perturbation theory. The non-perturbative parts are actually not very significant at all. So I have this, I forgot to turn off my notifications. So I have this nice truncation scheme, which I describe in a paper that will come out shortly, that tells you that I can actually solve the differential equation, not to infinite order, because I don't know how to do that, although there may be ways of doing it, but I can solve it to high enough order such that if you ask me a question at up to some given energy scale, I can give you arbitrarily good answers up to and including that energy scale. And so in that way, jumping back now to my my slides, I can show you some pictures, and then I'll be done. So what you do is you build these interpolating models in the way I've told you, and you solve the differential equation. Wrong thing. Sorry. Draft. There we go. And you solve the differential equation. So hopefully you can see this. And these are some examples of how this truncation would work. If I truncate, for example, just to some small values of k, like k equals 1 or 2 or 3, I'm only going to be able to access very tiny energies. And we've already seen that. If I just truncate to k equals 1, I'm doing the Airy model, and I'm just in the very, very tail infinitesimally of the whole story, which isn't enough. So I need to add in more models. And in fact, what I've been able to do is solve the interpolating model up to k equals 6. By the time you get to there, I'm able to access quite a lot of the energies. And in fact, anything beyond that is essentially just perturbation theory. And so I can solve the differential equation. It turns out that I need to solve a 15th order differential equation, but it turns out I can do that. It works out quite nicely. This is highly nonlinear, so you're using numerical methods to solve. And you can then solve for all of the eigenvalues and eigenfunctions. And so you now have a bag of, in some of these examples, of the order of, say, a couple of thousand eigenvalues for the problem, for which I can then go and build H explicitly using the formulae that I was telling you about, not H, the partition function, or correlation functions thereof. And so you're seeing this, you're the first group to see this in all its glory. Here is, in this way, the full non-perturbative partition function, where I've drawn for you the spectral density for the super JT models I was telling you about, or one of them. So the dotted line is that cosh root E over root E I was telling you about. There's the disk level produced by Stanford and Witten. And the red line is, I think, a couple of thousand points at which I know every energy and wave function, which I've computed, because I've essentially computed that U. I've computed essentially the potential of the JT gravity matrix model explicitly to all orders in perturbation theory and beyond the non-perturbative physics. And so there are all the non-perturbative wiggles. That's the analog of what you saw in the Airy model. Now I can use all of that. Now I have all of that. I can now go and I can compute higher order correlators. And so, drum roll. You're the first to see this. This will come out on Monday. Here's, for example, the disconnected part, which is essentially the partition function squared of the spectral form factor. And there's the connected part. So this corresponds to a picture that is quite familiar to many, particularly Juan, I think, where I have a wormhole type solution. This is the connected picture I drew for you before, that cylinder diagram with a partition function on either end, but then it's connected by a smooth geometry like this. Sorry, which you can't see because I haven't drawn the picture. But the beautiful thing is that this is not just the cylinder, this is everything. This is a cylinder with arbitrary number of handles and crosscats and beyond, non-perturbatively. The non-perturbative information is extremely important in knowing how this, let's see if I have my cursor back, no I don't, how this ramp, as this thing is called, this rising part of the spectral form factor, how that turns over. You cannot see in perturbation theory how it turns over into what's called the plateau at the end. you need the non-perturbative information. And so what I've done is I've computed that for you now in a number of JT gravity models, not toy models of like sort of generalizations of Airy, but the full model, which I think for the first time allows you to do this explicitly. And now we can study the spectral form factor. So there it is all together. This is the classic, I'm rooting for this to be called the saxophone because people keep using trumpets all over JT gravity. So this is clearly a saxophone shape. I'm rooting for that term to take hold. So you guys help me with that. But the key thing there is that I've computed for you and shown you the full non-perturbative spectral density and full non-perturbative spectral form factor, giving you telling you a lot of information about the model. And so I've done this for these JT supergravity models. I've also done it for ordinary JT gravity, regulated non-perturbatively in a way that I outlined earlier. And I think this technology is useful for other types of JT gravity as well. And there's a lot more you can do. It's easy to compute higher point correlators in this language, and so on and so forth. So I think in view of the time, I should stop there. But tell you there's a lot more to see. Please look out. I think on Monday it should come out for the paper, which shows you not just these results, but because I hope this is going to be a useful technique for people. I've put a lot of detail into how to actually solve these equations, do this truncation that captures essentially all you need without having to solve an infinite order differential equation. And so on that note, I'm going to stop and take some questions. And apologies for going on a little bit longer than I should have.
Thank you very much, Clifford.
In that finite plot, did you have a specific value of S0?
Yes. Yeah, no, great question. So in fact, this is very good. It's probably easier if I draw something. That particular what I essentially did in the calculations where I show examples is I turned remember S0 is essentially H bar, e to the minus S0 is H bar. I essentially was working at H bar equals 1 just to emphasize the non-perturbative features. So you can dial that down. You can put that whatever you want in. And in fact, some of the features you'll see then will connect to things that people know from perturbation theory. So the ramp, for example, becomes linear for very small H bar, and then you have this turnover, and you have the slope. Essentially, the slope of the slope is determined just by the disk level beta dependence of the partition function. So you can see all of that if you dial it down and match to perturbation theory. But the really exciting stuff for me is to really emphasize the non-perturbative stuff and see what that does. And so you see things like, for example, at moderate values of H bar, the linear part of the slope never shows up. The physics never has time for the slope to go linear before it starts turning over into the ramp. And you can really study all of that explicitly in this formalism. And so it's one of the reasons I think it's kind of exciting to be able to do that with this technology. Any other questions?
Did I also understand correctly that you were saying that the 1 over square root of E disappears, or there was a
right, yes. This is so nice. Let me. I think again. I think it's maybe better if because I can't point I'm gonna have to figure out what that is. I'm gonna draw pictures instead. But this is really nice. This was already seen. In a toy model of the tail of the eigenvalue distribution in Stanford and Witten. So you have. Let me try and match the colors I had before, otherwise it'll all get confused. Nope, there it is. So you have something like that. This is the cosh root E over root E. I'm suppressing factors of 2 and pi and etc. What happens is that in the in the 2-2 model, which is my favorite because it's more well behaved. In the 2-2 model, what happens is that the non-perturbative corrections kill that tail completely. In fact, it's even more dramatic than this, and it's one of the reasons that I focus on these two models. The fact is that there are no other perturbative contributions to the spectral density in these supersymmetric models, supergravity models. This is all there is, plus 0 for higher order corrections. So there's an H bar here on the bottom line. And perturbatively, there's nothing else. This was shown by Stanford and Witten as kind of a surprise that came out of some of their work. I can reproduce that surprise because it turned out I knew about that surprise back in 1991. I just didn't know. You know, it was a property of that equation I showed you, which now matches quite nicely with what they're doing. So it turns out then that you get non-perturbative corrections. All the corrections you get then are non-perturbative. There's not perturbative plus non-perturbative stuff in these models. So you really can kind of see a lot of what's going on quite nicely. And what it does, as I said, is it matches, and there's some wiggles, and then it goes away. In the case of the 2-2 model and the 0-2 model, instead, what you have is an enhancement. Excuse me. What you have is I drew it rather badly, but instead of going away, it stays there and in fact persists non-perturbatively. That's really, really nice because what you see is that in the spectral form factor, those features show up in a major way. The spectral form factor behavior in those two different models reflects a lot of what I told you. The existence of that bunching up of states, that accumulation of states near the end of the eigenvalue distribution contributes, for example, to making the ramp, the transition from the ramp to the plateau, take a very long time. Those correlations that usually wash away to get you up to the ramp fairly quickly in a typical model don't turn on as quickly. That effect doesn't turn on as quickly because of that weird tail that the 0-2 model has. The 2-2 model, on the other hand, because it's so spectacularly non-perturbatively different from its 0-2 cousin, then has a very different kind of behavior. You watch the ramp go up, and then it turns over very sharply into the plateau quite quickly. The rate of fall off, the slope behavior as well, is affected by this physics as well. And so the naive perturbative slope, the t to the -1 that you would normally get fall off in the supersymmetric model, is correct for 0-2, but for the 2-2, it actually can fall faster because those non-perturbative corrections change the neighborhood of the endpoint quite a bit. So you can see all of that quite beautifully. I explain all of this in the paper.
Okay, thank you.
Any other questions?
Okay, if there aren't any more questions, let's thank Clifford again. You can unmute and give him a round of applause.
Thanks, everyone. I hope that was
the awkward moment of the Zoom.
Right, yes, that's right.
Great, thank you for joining us.
Yeah.
Bye, Juan. Good to see you.
Goodbye. Bye, everybody.
Bye, everyone.
Good organization, Jeff.
See you later.
Bye.
Very good. Let me, so Clifford, perhaps we can continue our conversation for a little bit.
Yeah, I'd love to.
Right. Let's see.
Hopefully that was the right level. I can never
Yeah.
tell when it was a mixed audience. Yeah. Okay, good.
Yeah, I thought it was. I thought it was a good, very good level. Let me just. I just want to stop recording.
Oh right. Yeah.